Time for us to do some practice for problems which involve the second derivative. So there's a lot of concavity coming up in the next little bit here. As always, it's important for you to not just watch, but to do. Make sure you do as much as you can on your own. That's how you get better. And if you're watching the video and following along, make frequent use of that pause button and say, let me see if I can do this. And try it. And you know what? A lot of times, you'll be able to. You're better than you might think you are. And pretty soon, you're going to be amazing. But, of course, to get there, we need to practice. So, let's begin. Our first problem. Find all inflection points for y equals 9x e to the minus x squared over 6, and determine the intervals where the function is concave up and where the function is concave down. Now, whenever you see something that says inflection points, you know two derivatives are in our future, because the inflection points are determined by the second derivative. Really, what we're after is that the second derivative determines concavity, and inflection points correspond to changes in concavity. So we begin. We start with our function, y equals 9x e to the minus x squared over 6. Take our first derivative. So, product rule. Derivative of the first, 9 times the second, e to the minus x squared over 6, plus the first, 9x, times the derivative of the second. Well, the derivative of e to the minus x squared over 6, by the chain rule, e to something is e to something, times the derivative of that something. So here, it'll be minus 2x over 6, and really that would become x over 3. Now, before we take our next derivative, I think it's useful for us to simplify, because I don't want to think of these as three things multiplying together, because certainly I can combine the x's. So, what do we have? We have 9e minus x squared over 6. 9 and a third makes 3. The minus means we subtract. So minus 3x squared, because x times x, e to the minus x squared over 6. Good. All right. Now, next, second derivative. Y double prime. So for the first term, 9, and then the derivative of e to the minus x squared over 6, well, we've done that. So remember, multiply by the chain rule, minus x over 3. Product rule, derivative of the first, 6x e to the minus x squared over 6, and then minus 3x squared e to the minus x squared over 6 times the derivative of minus x squared over 6, which is minus x over 3. So, let's see, what do we have? Well, here, 9 and the third would really make this at minus 3x e to the minus x squared over 6. And on the end, the 3 and the third cancel. Minus minus cancels. So really this is simply x cubed e to the minus x squared over 6. Now, let's put it all together. So, what do we have? Well, that's, I'll put this term in front. We have x cubed e to the minus x squared over 6 minus 3x minus 6x minus 9x e to the minus x squared over 6. Now at this point, well, factor out what's in common. Definitely the e to the minus x squared over 6 is in common, but also the x. So we can factor out x e to the minus x squared over 6, and then we have x squared minus 9. Aha! Oh! After all the factoring we've done in recent sessions, this is going to be a very pleasant one, a very relaxing thing, because it's the difference of squareds, a squared minus b squared. So that factors as x minus 3, x plus 3. All right, good. Now, there's our second derivative. Now, essentially, we're looking for what you might call critical points. Where is this undefined? Where is it 0? Well, it's never undefined. These are all nice functions. Essentially, it's a polynomial here times an exponential function. So, all right, so we don't need to worry about being undefined. How about 0? we don't need to worry about this last part. In fact, e to something is always positive. So that's not going to contribute any zeros. So we have 3 candidates, 0, 3, and -3. Now, those might be inflection points, or they might not. See, the thing is they're potential inflection points, but you have to make sure that we actually change concavity at those points. So, to check, we should sketch. We'll sketch our number line here. -3, 0, +3. And we ask, well, what happens when we plug in values? So we're going to plug in values on the various pieces. So there's 4 chunks here. We test each one. And, well, let's go through it. Plug in something below -3. And say -4. That'll be negative, negative, negative. 3 negatives together tell us that our second derivative is negative. How about -1? Negative, negative, positive. All right, that says there's only 2 negatives, and therefore, combined, it's positive. Plug in +1. Positive, negative, positive. Well, there's 1 negative there, so we're back to being negative. Finally, plug in, say, 4. Positive, positive, positive. All right, finally, everything's looking up. Good. So, now, what can we say? Well, we're down, because our second derivative is negative. Then we're up. Then we're down. And then we're up. And so now we say, aha, they are all inflection points, because our concavity keeps changing at every single one. So, we're ready to put it all together and give our final answer. So here we go. Where are the inflection points? Well, they are at x equals -3, 0, and +3. But you notice they said, hey, and, which means there's more work. It says, where is it concave up? Where is it concave down? All right, so where are we concave up? We're looking for where the derivative is positive. So we can say, well, from -3 to 0, and from +3 to infinity. Where are we concave down? Okay, well, what would that be? That would be up to -3, so from -infinity to -3, and from 0 to 3. I will say that some people may or may not say, look, these should be included or they should not be included. In other words, square brackets versus parentheses. That's getting to sort of fine detail. Always check with your instructor. They'll let you know what they prefer. But that's the idea. 2 derivatives, set them equal to 0, and check on both sides to see what's going on. All right, good. A nice warm-up problem. There's many more to come, so we'll be well trained by the end. All right, next problem. Give a sketch of the curve f of x equals 4x cubed minus x to the fourth minus 11, and indicate the critical points and inflection points on the sketch. All right, well, we know what we need to do. It says we need to give a sketch, which means when we think of sketch, what we're going to think of is really industrial strength connected dots. Not industrial strength in that we're going to have many dots, but in that we're going to really get the really good dots, the points on the curve which are best explaining the behavior of what the curve looks like, which means we need to explore the first and second derivatives. Now, the good news is it's a polynomial, which means these are nice curves to work with, nice derivatives. Everything's clean. So here's our function. First derivative, f prime of x, would be 12x squared minus 4x cubed. Nice. F double prime of x would be 24x minus 12x squared. All right, well, that was pretty quick. Next, where are the critical points? Well, that's really when we say critical points, that deals with the first derivative. We're never undefined. Polynomials, beautiful functions. We love working with polynomials. Are we over 0? Well, okay. So if f prime of x equals 0, well, that tells us that we come up to here and we say, well, let's clean this up a little bit. Let's factor out x squared, and let's factor out a negative 4. That would say negative 4x squared times x minus 3. So the minus 3 because of the plus 12. Negative 4 times minus 3 plus 12 equals 0. So that says it's at 0 and 3. So these are our critical points, which means if we think of our dots of, when we play connect the dots, we're going to have 0 comma something, and we're going to have 3 comma something. All right, so those are our critical points. Now, the inflection points, we got to look at the second derivative. So let's take the second derivative and set that equal to 0, because that's where we could have our inflection points. So second derivative equaling 0, that would be, well, let's do the similar thing. Certainly we can factor out x, and let's go ahead and factor out minus 12. So minus 12x times x minus 2. Well, that says x equals 0 and 2. All right. So, hey, we already had 0. Cool. All right. Interesting. So 0, something must really be going on at 0. So now we have 2 comma something. All right. So when it comes to plotting this function, we really have 3 key points that we're going to need to understand. So let's figure out what are the y coordinates for these points. We've so far found the x coordinates. So 0 is the easy one. When you plug in 0, you get 0, 0, minus 11. And therefore, our y coordinate is going to be minus 11. All right. Now, the other ones we have to work a little bit on. Let's think about 3. So we'll have f at 3 would be 4 times 3 cubed minus 3 to the 4th minus 11. Well, 3 cubed is 27. 27 times 4 is 108. 3 to the 4th, well, that's 3 4 times, right? So 3, 9, 27, 81. All right, so that's 81 and minus 11. So, well, that's really, it's 108 minus 92 is one way to think of it, which gets us to 16. So, all right, well, not so bad. Could be a lot worse. Okay. Now, how about 2? Well, f at 2. What is that? 4 times 2 cubed minus 2 to the 4th minus 11. Well, that's 4 times 8, 32, minus 16, minus 11. Oh, okay, 32 minus 27 is 5. All right, good, good. Okay, well, now we know our points. So what do we do next? Well, the next thing for us to do is we need to understand our behavior. So, what does that mean? Well, let's go ahead and get a little bit further with our drawing here. So I'm going to mark our key points. So we have, say, 0, minus 11. So here's negative 11. We have at 2, 5. So let's say this here is at 2, comma 5. And then we have at 3 and 16. Well, that'd be roughly up here. Okay, so here's 16. All right, so there's our points. Interesting, interesting. Well, okay, let's see what happens. All right, now, oh, by the way, we should point out, as when it comes to drawing, these are places where our derivative equals 0. So I'm going to go ahead and at 0 and 16 do a little dot, 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 dot. and a little ... action here. Just to sort of help remind ourselves that, oh, hey, these are places where our tangent lines are horizontal. All right, now, got sidetracked. Let's get back to the real matter, which is what's the behavior of the function in the various pieces. And in particular, I'm going to split up at 0, 2, and 3. And I want to ask the question, what's happening to the first and to the second derivatives in each part? So we plug the points in. So, I don't know, plug in -1. If I plug -1 into the first derivative, well, what would that be? I can plug it in here. That would be 12 plus 4, which means that my first derivative is positive. Now suppose I plug 1 in. 12 minus 4. All right. First derivative is still positive. All right. Plug in something between 2 and 3. Now, that's a little bit more subtle, but I can use this form here. See, if I plug in 2.5, we have -4, negative, 2.5 squared, positive, and then 2.5 minus 3 is negative, 2 negatives, so I'm still positive. If I plug in something bigger than 3, you know, 1,000,000 or 4, or both work. But the point here, if I plug in something bigger than 3, I can see that the x cubed term will dominate, and that's a negative term, and so that is finally, we switch. So our derivative goes negative. All right, so that's our first derivative, second derivative now. All right, so plug in something below 0 into our second derivative, say -1, -24, -12. So second derivative is negative. All right, how about 1? What do we see? 24 minus 12. Positive. All right, there's a switch. All right. Okay, how about between 2 and 3? Okay, well, let's use our form here. 2.5. What do we have? Negative, positive, and a 2.5, that's positive. And therefore, this would be back to negative. How about at 3? After 3? Well, plug 4 in. And you could, or 1,000,000 or whatever. And you can see that x squared term will dominate as you get a very large number, and therefore it's negative. So we see, aha, our second derivative is negative. All right, now, why are we doing this? By understanding the behavior of the first and second derivative, it gives us an idea of what the curve should be looking like. So I'm increasing concave down. So if I'm increasing concave down, I have to look something like this. Now I'm increasing concave up. I have to look something like that. Increasing concave down. Okay, well, wait, yes, increasing concave down, yep. So I'm something like that. Decreasing concave down. All right, that means I have to look something like that. So these pieces here give us the shape for the various parts over here. So I'm thinking, okay, so here I have to have this type of shape coming up into this point. And I have to have a flat tangent line, so okay, I'll look something like that, roughly speaking. Between 0 and 2, I'm coming off the flat tangent line and heading towards this point, concave up. From 2 to 3, now I'm going to be concave down, and then I'm coming in at a flat tangent line. And then after 3, I'm going to head back down again. And there we go. There's a sketch. And it's not perfect. It probably needs to go down a little bit sharper, but it really captures the qualitative aspects of the function. We're really hitting the highlights of saying these are the points which are really important and the ones which give us the most insight into what's going on. And isn't it nice to be able to understand what's going on? I love it when that happens. Good. All right, well, let's try another problem. So, for the function f of x equals log of absolute value x plus 3 over x to the fourth, determine the intervals for when the function is concave up and when it is concave down. Now, if the absolute values are throwing you off, because I don't think we do this very often, I just want to note that the absolute values are there because it turns out that when you talk about the log function, log is only defined as a function if I'm plugging in a positive thing. So I can't plug a negative thing in. So by putting the absolute value, it says, hey, I can handle both positive and negative, still have a hard time with 0. And now it's a beautiful thing, easier to check by piecewise, that in general, the derivative of log of absolute value of x is 1 over x. If the absolute values are throwing you off, don't worry about it. Just think, whenever I take a derivative, 1 over the inside times the derivative of the inside. Okay, now let's think about taking this derivative. You might say, hey, I know this doesn't look so bad now. If I'm doing f prime of x, that would be what? Well, 1 over the inside times the derivative of the inside, which means, well, I'm going to be doing a quotient rule and more work. All right, now, generally speaking, we really don't mind more work, but we don't want to do too much work. We want to be smart. And when I say we want to be smart, we want to set ourselves up to not make errors. Because, well, I'll be honest, errors are almost inevitable if you keep doing enough math. They're going to creep in. So the key is error minimization. How do you stop yourself from making many errors? And the way you do it is to say, let me make sure I'm doing problems in a way which is least likely to introduce errors in the process. So how does that relate to this? Before I take a derivative of any function, there's always sort of a few seconds that should pass through your mind. We say, could we make this function easier to take a derivative of? In other words, is this really the right form that's been given? Now, this is especially true whenever you see a log, because log has lots of wonderful ways to rewrite things. And so, before we take any derivative, we should say, hey, you know what? Whenever I have log of a division, that becomes log of a subtraction. So I can say log of x plus 3 minus log of x to the fourth. And I say, hey, wait a second. Whenever I have a power inside a log, I can bring a constant down. So our function could also be written as log of x plus 3 minus 4 log of x. And that will be a much simpler derivative. Indeed, let's just take our derivative now. So we have f prime of x would be derivative of log of x plus 3, 1 over x plus 3, times the derivative of x plus 3, which is 1, minus derivative of log absolute value of x, that's right there. So there's a 4 times 1 over x. Aha! That's pretty good. And it turns out that we didn't have to do so much work. We didn't need that quotient rule. And, okay, good. Phew, less likely to make a mistake. Now, we do need to sort of get a little bit better handle on things eventually. But remember, where are we going for? We're not looking for increasing, decreasing. We're not looking for critical points. We're looking for concave up and concave down, which means keep taking derivatives. All right. Now, how do we take our next derivatives? It might be useful to think about what is 1 over x plus 3. In a very convenient way for calculus, it's x plus 3 to the minus 1. It's nice to have that exponent up here so that we can apply our rules. So minus 4x to the minus 1. So our second derivative would be, well, here, the minus 1 comes down, x plus 3 to the minus 2 times the root of the inside, which is 1. Here, the minus 1 comes down, so it'll become plus 4x to the minus 2. And there we go. All right, so we have 1 over x plus 3 squared plus 4 over x squared. And, oh, I forgot my minus there. There we go. Aha! Progress. Okay, good. Now, what comes next? Okay, well, the next thing for us to do is, of course, to clean this up. We want to understand things such as when is it undefined and when is it 0. Well, undefined, that's not so bad because we can see we have some fractions. So we can say, let me switch colors really quickly. You can say our second derivative is undefined at, well, -3 and at 0. Of course, that's not too surprising. See, -3 and 0 is when we'd end up putting some zeros into our log function. And when you put zeros into the log, that's usually going to be a bad thing. So we want to make sure that we avoid anything too bad. Okay, so make a note here, 0, -3. Now, how about f double prime equals 0? Well, for that, let's go ahead and put this over a common denominator. So we need to multiply the first term by x squared. So we have x squared over x squared times x plus 3 squared. And the second term by x plus 3 squared, so plus 4 times x plus 3 squared. Okay, so, well, that would be what? Minus x squared and plus 4 times x squared plus 6x plus 9. Divide that by x squared times x plus 3 squared, which would be, well, minus x squared plus 4x squared would be 3x squared. And then plus 24x, and then plus 36. Now, that's not looking great, but notice that all of these have 3. So that means I can factor out a 3. So we have 3 times x squared plus 8x plus 12. Now, does x squared plus 8x plus 12, does that factor in a nice way? And if so, how? Well, what do we need? We need two numbers that multiply to 12 and add to 8. I can think of two numbers that do that, 2 and 6. So this would be 3 times x plus 2 times x plus 6. Divide that by x squared times x plus 3 squared. Aha! So we get that our second derivative equals 0 at -2 and -6. So that makes our list. Good, good. So what happens next? Well, I mean, the next thing for us to do is say, look, we know the important points as far as the second derivative goes. It's the ones that we've listed here. So we need to draw our number line. So we draw our number line. And let's see, -6, -3, -2, 0. And now what we do is at every single point, we say what happens to the value. Now, some good news for us. Do you see the downstairs? X squared times x plus 3 squared? Always positive. Because I'm squaring. Now you might say, well, it could be 0. Yeah, but we're not gonna look at what happens at -3 and 0. So we really just need to say what happens in the numerator. So suppose I plug in a -7. Well, here I'll have a negative and a negative. Put that together, that says our second derivative is positive. All right, how about -5? Well, negative, positive, because -5 plus 6 will be 1. So that says our second derivative is negative. Okay, how about between -3 and -2? Negative, 2.5, if you will. Well, negative, positive. So still negative. All right. How about between -2 and 0? Well, I'll say -1. -1 plus 2 is Positive. Negative 1 plus 6 is positive. So we're positive. How about above 0? Okay, definitely positive. All right. Good. So what do we see? Well, we see we are concave, and we can make some notes here. We're up, down, down, then we're up, and we're up. Now, can we combine? Because you see how we are up and up? Is it possible for us to say, oh, let's just merge them together? And why not? Well, the reason we can't do it is because our function isn't defined at -3 and at 0. It's where we, in particular, we're going to have asymptotes there. So we can't merge things together. All right, so what's our answers? Well, it's going to be a long list here. All right, so concave up will be what? Well, we'll have below -6, so we go from -infinity up to -6. And where else do we have? Well, from -3 to -2, so from -3 up to -2. And, oh, -3 should be a parenthesis because that's not a point of our function. All right. That's not up. That's, sorry. Here's up. So, from -2 up to 0. And from 0 all the way to infinity. Okay, so there's our concave up. And then concave down. So, I should get bigger paper, shouldn't I? Well, okay. Maybe smaller pens. That could help. Okay, where are we down? Well, from -6 all the way over to -3. Don't include -3. Then from -3 all the way to -2. But -2 is okay to include. Okay, so, and there you go. That's the answer. Cool. Cool. Good stuff. Good. Well, let's try another problem. Hey, how about that? Okay. So, we're told the functions f and g are both defined on the interval from -5 to 12. On this interval, f is positive, decreasing, and concave up. G is negative, increasing, and concave down. And there's a new function called h of x, which is f of x squared plus g of x squared, and still the same interval. So there's two parts, parts A and B. The first one, determine, if possible, whether h is increasing or decreasing. And then part B, determine, if possible, whether h is concave up or concave down. All right, so let's start by reading off what we have. Because they're using these words, let's turn it into a different way to think about it. So we're told f is positive. So I'm going to say f positive. Decreasing. Now, when we talk about decreasing, that's telling us something about the derivative. In particular, it's telling us that our derivative is negative. Concave up. Well, that tells us our second derivative is positive. So our function is positive, first derivative is negative, our second derivative is positive. How about g? Well, we're told g is negative, so g is negative. It's increasing, which means the derivative is positive, and it's concave down, which means our second derivative is negative. All right, now let's get to part A. I'm asked to determine, am I increasing or decreasing? Well, we know, if we want to know increasing, decreasing, we look in the derivative. So we're going to start by saying, what's happening with our derivative? So what is happening? What is h prime of x? So we do our chain rule. So that's 2 times f of x times f prime of x, right? Because the 2 comes down, f of x to the 1, that's my f of x, times the derivative of the inside, f prime of x, plus derivative of g of x squared. Similar process. The 2 comes down, g of x to the power 1, which is g of x, times the derivative of the inside, g prime of x. All right. Now, here's what we need to do. Let's check our signs. Okay, so let's see what we have. What do we know about f of x? Well, we know f is positive. So this is a positive number. What do we know about f prime? F prime is negative. So we have a negative number. How about g? G is negative. Okay, so that's a negative number. G prime is positive. So that's a positive number. So when you multiply a positive and a negative, the result is this is a negative quantity. That's a negative quantity. And therefore, when we combine two negatives, the result is a negative quantity. Okay, so we know h prime of x is negative. All right, well, if h prime of x is negative, what's our conclusion? Our conclusion is our function h is decreasing because our derivative will always be negative. Good. All right. Now, that's part A. Well, but we also have a part B. So let's try that one. Okay, so for part B, well, we need the second derivative, right? Because it's asking about concave up, concave down. That's the second derivative. So we need to take another derivative, h double prime of x. So what would we have? Well, product rule, derivative of the first, f prime of x times the second, derivative of the first times the second, plus the first, 2f of x times the derivative of the second, which is f double prime of x. Do the same thing here. Derivative of the first, 2g prime of x times the second, g prime of x, plus the first, 2g of x, times the derivative of the second, g double prime of x. All right, so those are all the terms. There's a bunch of terms. But again, let's go through it term by term, see what we know. F prime, negative. So we have a negative times a negative. F, positive. So that's a positive. F double prime, positive. All right, positive. G prime, negative. Oh, sorry, G prime, positive. Actually, I'm pointing to G. G prime. All right, positive, positive. Now G, negative. G double prime, negative. Now what do you see? Well, if I multiply two negatives or two positives, the result is always positive. So I see a positive, 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 and therefore everything's positive, so the whole quantity is positive. Well, so if h double prime is positive, what does that say about our concavity? Well, that tells us that we are going to be concave up. All right, so there we go. Decreasing, concave up. All right, nice. So even though we didn't know the function h, really the key here is questions such as increasing, decreasing, and concave up, concave down are not about the values, they're about the signs. And we did have enough information to determine the sign. We saw the sign, and it opened up our eyes. We saw the sign. All right. Well, good. Let's try another problem. So, determine the intervals when f of x, which is 7 times arctangent of x, plus x times the natural log of 1 plus x squared, is concave up and concave down, and list all the inflection points. Now, before we start, we should know that this is a function which really has no issues. Arctangent is defined for all values, so woohoo! Good job, arctangent! It's a great function. Also, notice we're plugging 1 plus x squared into log. Well, 1 plus x squared is always at least as big as 1, and therefore we don't have any problems. See, log, the real problems with log are when we have 0 being plugged in, or if we have negatives, but nope, we're good to go. So this will be defined for all x, and I suspect the derivatives will be as well. So, all right, good. But of course, we don't want just one derivative. We want two because we're asked about concavity. But of course, to get to the second derivative, you got to visit the first one along the way. So we begin. F prime of x. Well, derivative of arctangent, that's not so bad. 1 over 1 plus x squared. Now here, we have to do a product rule. So the derivative of the first would be 1 times the second, the natural log of 1 plus x squared, plus, then I have here the first, x, times the derivative of the second. Well, that would be 1 over 1 plus x squared, because we're taking the derivative of log, so it's 1 over the inside, times, by the chain rule, the derivative of the inside, which is 2x. Okay, so let's clean up this derivative. Since we're going to take another derivative, it's often helpful to say, maybe we'll clean it up before we take our next derivative. See, I notice that I have two terms with 1 plus x squared in the denominator. Let's throw those together. So if we did that, well, here we have a 2x squared, and there we have a 7. So 2x squared plus 7, divide that by 1 plus x squared, and then, of course, plus the natural log of 1 plus x squared. All right, now we're ready for our second derivative, f double prime. So, well, we'll do a quotient rule here. So what do we need to do? We're going to take the bottom, 1 plus x squared, times the derivative of the top. Well, that would be 4x, minus the top, 2x squared plus 7, times the derivative of the bottom, 2x. And all of that over the bottom squared. Now that's just the first term. Don't forget the second term. Derivative of log of 1 plus x squared. Well, we actually did it before. 1 over the inside, so 1 over 1 plus x squared, times the derivative of the inside, so times 2x. Now, we see here that they're almost the same denominator. The difference is this one is being squared, that one isn't. Not yet. So what do? Well, we don't square it, but we sort of get it up to that point. So I'm going to multiply here on the second term by 1 plus x squared over 1 plus x squared. And now we have a 1 plus x squared squared, which means we can combine. I do have to multiply from top and bottom because I have to multiply by 1, so I don't change anything. So now we can get one big happy fraction. All right, something over 1 plus x squared squared. All right, well, what is the something on the top? We work through it carefully. So distribute through 4x, so that would be 4x and plus 4x cubed. Now the next, don't forget this minus, and we distribute the 2x, so that would be a minus 4x cubed and minus 14x. And then what do we have? Well, 1 times 2x times 1 is a 2x, and 2x times x squared is 2x cubed. All right. Well, let's hope we get some simplification. After all, we want things to simplify. It always is great when things get simpler. And in some sense, that's really what we've been training ourselves to do, is we're saying, hey, how can we take things that look complicated and turn them into things that look less complicated? And repeat, and repeat, and repeat. And eventually, if we do it often enough, things get pretty reasonable. In some sense, yeah, that's what math is, a series of simplifying arguments. So, well, upstairs, there's a single term with an x cubed left, and we have 4x minus 14x, that would be negative 12x, plus 2x, so that's minus 8x. Divide that by 1 plus x squared squared. We're getting pretty reasonable here. On the top, factor out a 2x. 2x times x squared minus 4. Divide that by 1 plus x squared squared. And x squared minus 4. Nice. See, that's the difference of squares, which means beautiful factoring is about to occur. So 2x times x minus 2 times x plus 2. Divide that by 1 plus x squared squared. All right. Now we're ready to talk about where do we start looking? Well, we don't need to worry about the denominator. It's never going to be 0. When can the numerator be 0? So our second derivative equals 0. That's the numerator equaling 0 at x equals 0, 2, and negative 2. All right, so we need to draw our points here. So there's 3 potential points. -2, 0, and +2. Okay. Now, what we need to do is say, hey, what happens on each side of these points, or in between the points? So, well, we plug it in. Now, when we plug it in, we really don't need to worry about the denominator because this part here downstairs is always positive. So, we're really going to say what happens upstairs. So, suppose you plug in something like -3. Negative, negative, negative. 3 negatives, meaning our second derivative is negative. Or if you like, we're concave down. How about -1? Negative, negative, positive. All right, there's only 2 negatives. Multiplying makes it positive. Concave up. All right, how about 1? Positive, negative, positive. 1 negative. So that's going to make the whole thing negative. So we're back to being down. All right, how about, say, 3? Positive, positive, positive. Good. Best part, all positive. So concave up. All right, so what can we say? Well, our goal was find all the intervals where we're concave up and concave down. This is going to tell us our answer. We just have to write it in sort of a more friendly notation, depending upon, of course, how they want our answer written. So what can we say? Well, all right, so we have concave up, concave down, and we should say our inflection points. Now, the inflection points are easy. Anywhere where we change concavity is an inflection point, and so there are 3 places, -2, 0, and 2. We change concavity on each one of those points, and they're points of our function, so they are inflection points. Where are we concave up? Well, -2 up to 0, so -2 less than or equal to x less than or equal to 0, and from 2 onward. So 2 less than or equal to x less than infinity. Where are we concave down? Below -2, negative infinity less than x less than or equal to -2, and between 0 and 2, 0 less than or equal to x less than or equal to 2. And there we go. We've identified all the places where we're concave up, concave down, and also our inflection point. Good. Whew. Did it all. All right. We're getting a lot of algebra practice. But of course, it's good to get algebra practice. All right. Next problem. So, let f of x equal 5e to the 3x plus 3 times cosine of 4x minus 6 times sine of 2x. All right, sure, why not? So, part A. Use the linearization of f of x at x equals 0 to estimate f of 0.05. Okay, well, let's just start with part A. Now, part A is linearization. Now, that deals with a topic we've talked about before. So the question is, do we remember what it means to talk about a linearization? And hopefully we do. As a quick refresher, linearization is really just a fancy way of saying tangent line. So what is it we're doing? Well, we're going to use the tangent line of the function at x equals 0 as a stand-in for our function. And we'll use that to get an estimate for what's happening to our function at 0.05. Okay, so, well, tangent line, what do we need to know? We need to know our function at 0. Well, that'll be 5e to 0, 5, plus 3 times cosine of 0. Cosine of 0 is 1, so plus 3. Minus 6 times sine of 0, well, that's 0. So that's 8. Now, we also need to know f prime of 0. which really says we need to know what f prime of x is. Okay, so the derivative of 5e to the 3x, well, the derivative of that would be 15e to the 3x. The 15 coming because we have the 5, and then the chain rule says we're going to have to multiply by the derivative of 3x, so that's where the 3 comes from, 5 times 3 being 15. Derivative of cosine is minus sine. So minus, and then there's a sign. The inside stays alone, but times by the derivative of the inside, so means we're going to have to multiply by 4. We already have a 3. 3 times 4 gives us 12. Okay, all right. Then the 6 sine 2x. Derivative of sine is positive cosine. There is a negative, so still negative. And then what do we have? Cosine 2x, because you don't change the inside, leave it alone. But multiplying the outside by the derivative of the inside, which would be multiplied by 2, there's already a 6, so that would get us to 12. So f prime is 0. Well, that would be 15e to 0, which is 15. 12 times sine is 0, well, that's 0. 12 times cosine is 0. Cosine 0 is 1, so that would be 12. So 15, 0, minus 12. And so we get 3. All right. Well, actually, that's pretty nice. So our tangent line would be y equals, in general, this is the form, f of a plus f prime of a times x minus a. In our case, a equals 0. So for us, it would be 8, because there's that 8. And our derivative at 0 is 3. So 8 plus 3x. Okay, so this is part of our answer. Well, that's it's not our answer, but it's how we get to our answer. That's the linearization. So that says that near 0, f of x is approximately 8 plus 3x. So 0.05, that's near 0, right? Is it? We'll get to that. All right. F of 0.05 is approximately 8 plus 3 times 0.05, which would be 8.15. Okay, now that is our answer for A. Yeah, this is a tool to get to that. Okay, A is done. We know our estimate. All right, now on to part B. So what does part B say? Well, it says find f double prime is 0. Okay, well, time for our second derivative. So we took our first derivative. Second derivative should be pretty similar. So f double prime of x would be 45 e to the 3x. Again, you bring the 3 down. Now here, derivative of sine is cosine. So minus cosine, inside stays alone. 4 times 12 is 48. And then here, derivative of cosine is negative sine. There's already negative, so plus. And then we'll have a sine of 2x. We're going to multiply by 2 on the outside times 12 gets us to 24. Okay, so there's our second derivative. Now plug in 0. F double prime of 0. Well, 45 e to 0, that's 45. Minus 48 plus 0 is negative 3. Oh, okay, that's not so bad. It's not bad at all. All right, so there we go. There's our answer for part B. Now, the interesting thing, how do part A and B connect? So, now we turn to part C. Okay, based on the answer to part B, which was negative 3, should we expect the answer for part A, 8.15, to be an overestimate or an underestimate? Okay, so how do we think about this? Well, what we have is that our tangent line looks like this. So here's our tangent line. So there we go. There's our tangent line. Now, the question is, what's the function doing? Because the function is near the tangent line, but it's not on the tangent line. It's going to start to verge off. But which way does it go? Well, that's where the second derivative comes into play. It's negative. a negative second derivative says that from the point of tangency, which is this point right here, I'm going to be going underneath. So that nearby 0, I should be underneath this tangent line. Now, when we got our estimate, which was here at 0.05, what did we do? Well, what we did is we plugged it in. And we said, let's use the tangent line as a standard for the function. So if we expect the function to be underneath the tangent line nearby, then we would say, hey, our estimate appears to be an overestimate because our tangent line is over what the function is doing at 0. So for part C, we would guess an overestimate. All right. Good. All right. Now, you might be wondering, there's one word here that you might say, suspicious. We used the word should. Now, why did we use that word should? The thing is, we can't say with certainty that at 0.05, we are an overestimate. And here's the crazy thing. If you plug this in other words, 0.05 into this function, it's an underestimate, not an overestimate. And that might make you feel uncomfortable with the logic that we just did. So I want to explain that if you go and check to see, hey, wait a second, it was an underestimate, what did we do wrong? I want to explain what happens. Remember that the moral of calculus is that we're understanding things near our point of interest, usually our point of tangency. And as we move out, away from it, we lose information. Essentially, we only have information at the point of tangency, and we have some idea of what's happening near the point of tangency. But as soon as you move away, you lose because information gets evaporated. It turns out, and not obvious at all, that if you look on this curve at approximately 0.015, that's an inflection point. So even though it's negative, in a very short time, it turns positive, the second derivative, which means that we're starting to bend back in the other direction. So because we're so close to an inflection point, microscopically close, you might not even be able to sense it if you were to plot it, unless you zoomed in quite a bit. Then that's why our error, even though we think it should be an overestimate, it turns out that because we are far at 0.05, it, in this case, was wrong. That's okay. That's all right. We are trying our best to see what should happen. And of course, there are ways to get better estimates. That's a fun topic. Calculus, too. It can be a great time. All right. Good. Well, hopefully that doesn't shake your faith. It shouldn't be, because it's a beautiful idea. Beautiful ideas. All right. On to another problem. Okay. Let h of x be the function e to the power 2x plus ae to the x plus b times x, where a and b are constants to be determined. So in other words, we don't know what a and b are. We got to figure it out. A puzzle. Okay, part A. Given that the function is decreasing only for x between 2 and 5, determine a and b. Okay, now we see, of course, the key word, decreasing. What does that tell us? Well, what it tells us is something about the first derivative. Okay, so you might say, wait, why are we talking about the first derivative kind of thing? Well, we also see that there's an inflection point coming up here. Okay, but let's get to that in a little bit. Okay, so decreasing tells us that we need to have our derivative is negative. Now, notice it's decreasing only between 2 and 5. So intuition says, all right, if I plot my line, here's 2, here's 5, then what's happening is I have to be decreasing only between 2 and 5, which means that otherwise I should be increasing. Now you might say, couldn't we be flat? No. The only way you can be flat is if you're constant, and this is not a constant function. All right. So there's our sort of behavior of the function. But we can translate this, of course, into information about the derivative. So increasing tells us something about the derivative being positive. So our derivative is going to be positive. Decreasing, derivative is negative. And increasing, derivative is positive. Now, what does that tell us about 2 and 5, where we transition between different behaviors? What it tells us is that our derivatives at 2 and 5 have to be 0. So for part A, what we really are told is that, hey, by the way, f prime of 2 equals 0 and f prime of 5 equals 0. All right, so that's what we can use to figure out what are A and B. We have really 2 pieces of information, and I have 2 things I have to figure out. That's good. However many things we have to figure out, that's how much information we need. So let's dig into our first derivative, right? Whoops, I said f, but these are h. Put these as h's here. No one notices that, right? Those are just very curious looking h's. All right. Okay, there we go. All right. Now, here we go. H prime. H prime of x is chain rule 2e to the 2x. A is a constant, so it's derivative of e to the x, and derivative of b times x will be b. Okay, so that's h prime of 2 would be, well, 2e to the 4 plus a e to the 2 plus b. H prime of 5 would be, well, 2e to the 10 plus a e to the 5 plus b. And equals 0 equals 0. All right, good. Well, 2 equations and 2 unknowns. Of course, it's a little bit more interesting than just our normal 2 equations and 2 unknowns, because we get some strange numbers, powers of e floating around. All right, does that change our approach? No, it doesn't change our approach. It's always a similar idea. You know, how do we combine things to get cancellation, simplification? That's what we're after. Simplify, simplify, simplify. All right. Now, there is an easy simplification. Notice that they both have plus b's. So, one thing we could do is just say, let's cancel the b's. And we can do that by carrying out subtraction. So I'm going to subtract. So I'm going to subtract, well, we'll subtract the bottom from the top. Why not? So that would be 2e to the 4th minus 2e to the 10th. And then that's the first term, plus a, and I'll just subtract these pieces, e squared minus e to the 5th, and the b's cancel, and 0 minus 0 is 0. All right, nice. All right, cool. So, well, can we go any further than that? Well, of course we can. Come on, we got this. All right, so we can write this as a times e squared minus e to the 5th is equal to minus 2, and I'm just going to pull out a 2 here, e to the 4th minus e to the 10th. Now, at this point, you might say, okay, we'll divide. And at this point, we're going to divide. Good, see, you're getting it. Ha! You knew what to do. All right, so minus 2, e to the 4th minus e to the 10th. Divide that by e squared minus e to the 5th. Now the next thing we're going to do is not totally obvious, because it feels like it's like, well, I guess that's as far as we can go. But we're going to do a little bit of flexing our algebra skills here. And we look at this and say, the top is kind of close to the bottom. It's, e to the 4 minus e to the 10th. Here's e squared minus e to the 5th. And what's the difference? Well, you're off by factors of 2. You know what you can do then? You can write this as minus 2 times e squared squared minus e to the 5th squared, right? That's e to the 4th, e to the 10th, over e squared minus e to the 5th. Now, what happens next? Can you see it? It's the difference of squares. So that says we can really write the top as e squared minus e to the 5th, which is a minus b, e squared plus e to the 5th, a plus b. All right. Well, the e squared minus e to the 5ths cancel, and we're left with something which is actually, well, maybe not the most obvious, not so bad. So minus 2 times e squared plus e to the 5th. So again, that's our a. So how do we get b? Well, to get b, now that we know a, just plug it into one of the two equations. Doesn't really matter which one. So let's say we plug it into, let's plug it in here, the first equation. So we can say that 2e to the 4th plus, here it's minus 2 times e squared plus e to the 5th times e squared plus b equals 0. Now, if we multiply this out, that's 2e to the 4th minus 2 times e squared is minus 2e to the 4th minus 2 times e to the 5th times e squared is minus 2e to the 7th, and then plus b equals 0. And, we must be doing something right. We've been living a clean algebra life. The e to the 4th cancel. Wow, that's beautiful. It really is. It's so clean how it all works out in a nice way. All right, so finally, move that term across, and we get that b is equal to 2e to the 7th. Nice. Good. So we've now solved for a and b. All right, now we're ready to move on to the second part of this problem, which is, given that we found a and b, find the inflection point. Okay, well, we continue by taking our second derivative. So, what would our second derivative be? Our second derivative would be h double prime of x would be here 4e to the 2x, and then plus ae to the x, I'll just leave it as ae to the x for now, and the root of b is 0. Okay, so we're looking for the inflection point, never undefined, so that's good news for us. So we're looking for when it's 0. Now, e to the 2x is really e to the x squared. It's similar process to what we did here, right? And so what we can do is we can factor in e to the x out. So e to the x times 4e to the x plus a. And, well, the e to the x, that can never be 0. So that says, hey, this is the part that has to equal 0. So we have that we need 4e to the x plus a equals 0, or we could say 4e to the x is equal to minus a, or we could say e to the x is minus a over 4. Well, hey, let's just put in what a is now. So I'm really multiplying this by minus a fourth, which it would be 1/2 e squared plus e to the 5th. So finally, that's what e to the x is. So how do I get x? Well, the answer is x is the natural log of 1/2 times e squared plus e to the 5th. Aha! That's our inflection point. Just as we would have thought, right? Well, maybe not. So, well, it's good that we did the work. Good that we did the work. All right. Well, on to another problem. Okay. There we go. The graph below shows the derivative, f prime of x, of a continuous function. All right, see how they emphasized the word derivative? They didn't want us to be confused. Not that that would ever happen. Okay. Now, answer the following questions about the function f of x. It's a continuous function. And provide complete explanations for your answers. Well, we'll see what complete means. All right, so part A. Identify the open intervals on which f of x is increasing and decreasing. Now, we know that here we can say f of x increasing means what? Well, when f prime of x is positive, and so we come over here and say, when is f prime positive? Well, f prime is positive when I'm above the axis, because this is f prime. This isn't f, it's f prime. So I say, okay, well, it's positive, well, from -1 to +1. There are numbers here, but there's a little grid here. So -1 to +1. So -1 less than x less than 1. They want open intervals. Because they know that there are people who are like, well, maybe it should be open, maybe it shouldn't be open. And then let's see, there's 2, there's 3, and then for x above 3. F of x is decreasing. Well, similar idea. When our derivative, f prime of x, is negative. So now we're saying, when is our derivative below the axis? Well, it's certainly when it's the case that we're below 1, below -1 for this part, and for this little blurb between 1 and 3. See how we just dip a little bit down? So therefore, it's negative. All right. Now, part B. Identify and classify the x-coordinate of any critical points. Okay, so where are our critical points? Critical points will be, the critical points are where derivative is undefined. Now, do we see any place where our derivative is undefined? Well, here, there's definitely a problem. So that's at x equals -1 and f prime equals 0. All right, does that ever happen where the derivative is 0? Well, I can see any place where I cross the axis here. So at 1 and 3. So x equals 1 and 3. All right, so there we go. We've now found our critical points. There's 3 of them. But now we have to classify. Now, here, you have to use the first derivative test on this first critical point at -1, because there's no way for us to apply the second derivative test, because the second derivative test says you have to have the first derivative equals 0. And so let's just throw in the first derivative test. So by first derivative test, well, let's see what we have. And we'll do a little bit of a picture here. I like pictures. So we're going to mark. We have -1, +1, +3. And we're just going to look at the sign of the derivative. So we're negative, and then we're positive. Isn't this easy? You have a picture, you can read the answers off. Then we're negative, and then we're positive again. So we alternate. Negative, positive, negative, positive. So that says we're going down, then up, then down, then up. So -1 and 3 are local mins, because you can see at those places down, up, while 1 is a local max, because what do we see? Up, down. All right, good, done. With that part, one more to go. Okay, so on to part C. Identify the open intervals on which f of x is concave up and concave down. Now, one of the things we can do is we can plot the second derivative, or we can think about what concavity means. So we can say concave up means what? Means that f prime is increasing. All right? So when does that happen? So we're looking for when are we going uphill? So we are going uphill as we move. So as we move from left to right, we're going uphill. So we're up, 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 and then we stop going uphill. So that's at -2. So we're going to say x below -2. Then we're going down. Then we're going down, and then up. Here we switch up behavior again. See, up, 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 up. So that's here at 2. So x below -2 and x above 2. That's concave up. Concave down, well, what would that be? Well, that would be f prime decreasing. So we're going downhill. Okay, so when are we going down? Well, from -2 to -1, we go downhill. And also from -1 to 1, we go downhill. But what do you notice? We can't go from -2 up to, not -1 to 1, it's -1, to 2. Aha. Got to be careful at that point. Now, notice we can't say from -2 to 2 because we're not always going down. See, there's this gap here, this discontinuity where we jump up, and therefore we can't merge them together. So it is proper to keep them separately. All right. Well, okay, cool. That was good. This is one of these problems where it's like, all right, we're not going to give the function explicitly. We'll give you some information about the function. In this case, store it as a graph and say, what can you tell us about the function? All right, it's good to be able to know this. This is, again, the qualitative sides of derivatives. Do we know what we're learning from these derivatives? Okay, our next problem. Good. Find and classify all the critical points on the curve y equals x to the 7/3 plus 7x to the 4/3 plus 28x to the 1/3. Also determine the intervals for which the function is concave up and concave down. All right, we've done these problems a lot, right? So we're probably going to get pretty good at these. So, let's begin. All right, so we have our function y equals, and the good news is, as functions go, it's not so bad. It's not really a polynomial. So even though it's always powers of x, polynomials are reserved for when the powers are whole numbers. We have fractions up in the exponents. But they're pretty good. As far as functions go, they're pretty good because they're fairly straightforward to take derivatives of. So, for instance, y prime would be the 7/3 comes down, x to the 4/3. And then the next term, 28/3, because the 4/3 comes down times 7, and then x to the 1/3, subtract 1. And then here, 28/3, because there's 28, the 1/3 comes down, x to the -2/3. All right, and while we're in the mood for taking derivatives, let's just go ahead and take our second derivative. We have to at some point. Why not now? All right, so the 4/3 comes down, 28/9, x to the 1/3. Then 28/9, then it's x to the -2/3. And then minus 56/9, x to the -5/3. All right, well, okay, I see some factoring in our future. All right, well, let's start with our critical points. So that means we really need to get a better handle on y prime. Now, I see definitely thirds. In fact, let's go ahead and pull out a 7 because 7 divides into 28. And let's pull out the lowest powers. So we have 7/3 x to the -2/3. And then When we pull that out, well, since we're pulling out x to the minus 2/3, to find our new exponent, just add 2/3. In other words, think of it as subtracting negative 2/3. So that would be x to the 6/3, which would be x squared. And then here, x to the 3/3. And then don't forget, you have a 4 remaining because we only pulled out 7 out of the 28. So 4x, and then here, plus 4. Okay. Actually, x squared plus 4x plus 4, that's nice. That factors in a very nice way. It's a perfect square. So it factors as x plus 2 quantity squared. Let's do the same thing for our second derivative. So, well, here we can definitely pull out a 9, and 28 goes into 56, so we'll pull out a 28 ninths, and then the lowest power would be negative 5/3, and when we do that, okay, add 5/3 to your power, so that would be x squared. Here be plus 3/3, so plus x, and here it'll be a minus, and 2, because we only pulled out 28 out of the 56, and then we pulled out the x to negative 5/3. And that factors. We are in luck. Look how everything factors. People like us when they write these problems. Okay, x to negative 5/3, and then we have our, let's see, it's going to be x plus 2x minus 1. I think we can check x squared, that's good, minus x plus 2x plus x, that's good, and minus 2. All right, good. Progress, progress. Now, what comes next? Well, let's talk critical points. So where are our critical points? There's 2 of them. If I plug in 0, I have an undefined, and if I plug in negative 2, I get 0. So we have critical points are at x equals 0 and at x equals negative 2. Now to classify them, because we have a place where the derivative is undefined, we don't want to use the second derivative test. So we're going to do the first derivative test at least for 0. Might as well do it for negative 2 as well. And in fact, you can see at 0 we have to, because look, it's undefined. Can't even use it. And at negative 2, what do you see? When I plug negative 2 in the second derivative, what do I have? I have 0. Well, if our second derivative is 0, what does that tell us? It tells us nothing. So the second derivative is really terrible as far as the test for the critical points here. But the first derivative is great. All right, now this is going to be really, really easy to apply our first derivative test. Why? Look closely. What do you notice? You have something squared. That's always going to be positive. But this x to the minus 2/3 is also a square. You can think of it as x to the minus 1/3 quantity squared. So this is positive. This is positive, which tells us what? It tells us that our derivative is always positive. So we're always going up, 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 up. Great. Okay. Interesting. So we're moving up and up and up and up. Now, okay. Well, what do we do with that? Well, what does that tell us about the critical points? Because it said classify, right? So if we're always going up, that says that both these points are neither max or min. Okay, interesting. So this is a function always moving up, always on the rise. Well, let's think about the other part. Concave up, concave down. So, well, we need to figure out where can we switch concavity. So we say, okay, when is the second derivative undefined or 0? So potential inflection points are at 0, negative 2, and 1, because undefined, 0, and 0. So, let's see, we'll sketch. So we'll put those in order, -2, 0, and 1. Now, let's make some observations. This is x. See how these are odd pieces upstairs? If I plug a negative number in, and if I take it to an odd power, it's still negative. If I take it to an odd root, it's still negative. So this will be negative when x is negative, and it'll be positive when x is positive. Useful to keep in mind. So if we plug in -3, negative, 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 3 negatives tells us that our second derivative is negative. If I plug in, say, -1, negative, positive, negative. So our second derivative is now positive. Say a half. Positive, positive, negative. Okay, which means that we're going to be to negative. Plug in, say, 2. Positive, positive, positive. So we're back to positive. So we alternate. Here, negative, then positive, then negative, then positive. Or, if you do it in terms of concavity, concave down, concave up, concave down, concave up. So we have interesting things happening where we're switching from concavity down, up, down, up. And so, well, when are the intervals? Okay, so we have to list. So for up, we're going to be from -2 up to 0. So, all right, this says -2, 0. And this is a personal preference. I know if you've been watching, you're like, Steve, wouldn't you normally include 0? 0 is kind of a strange point. So I'm going to wax philosophic for a moment here. I hope you'll forgive me. The reason I want to be really careful here is that 0 is a point on the function. Absolutely. There's nothing wrong with 0 because there's no negative exponents in the original function. 0 is not a point on our derivative because we have that negative exponent. And when we talk about, concavity, we really are saying what's happening to the derivative. And since the derivative isn't defined at 0, we really can't include the conversation. So that's why I wouldn't include 0. All right. Now, back to writing things up. And then we have from 1 all the way up to infinity. Concave down. Well, up to -2. So minus infinity to -2. And then from where? Well, we are going concave down from 0 to 1. So 0 to 1. And there you go. That's it. That's what's happening. All right. Good. Good. Interesting. Interesting. All right. Well, one more problem. Okay. Our last one. Let's make it a good one. All right. Ooh, sketch. Sketch the function y equals 2x over x squared plus 4 and mark any local, max, min, and inflection points. Okay, so sketch, meaning connect the dots. So we got to really get a handle, where are the important points? Which means let's explore the first and second derivatives. So we'll start with our first derivative. Well, here I see a rational function, so probably we'll use the quotient rule. So the bottom, x squared plus 4, times the root of the top, 2, minus the top, 2x, times the root of the bottom, 2x. All of that, divide that by the bottom squared. Good. All right. Well, before we go further, let's clean it up. So what can we do? If we multiply out, we'll have 2 times x squared, but then we also have a minus 4x squared, so that's minus 2x squared, and then 2 times 4 will be plus 8. And divide that by x squared plus 4 squared. So second derivative will be what? Well, the bottom, x squared plus 4 squared times the root of the top, minus 4x, minus the top, minus 2x squared plus 8, times the root of the bottom, 2 times x squared plus 4 to the 1, times the root of the inside, 2x. All right, good. See, it's a function, x squared plus 4, inside a function, square. So you got to make sure you got all your levels of your chain rule, all of your little pieces of onion. Over the denominator, your bottom term, squared. Okay, now let's clean that up because we really want to get a handle on what's happening to this. Where is it 0? Where is it undefined? Actually, let's do the undefined. Is this ever undefined? And the answer is no. There's no problems because the only thing we might be worried about is the denominator, but x squared plus 4 is positive. Life is good. Life is great. So, good, never undefined. We can spot in our second derivative that really, look, we have an x squared plus 4 in every piece. So we're going to knock out one x squared plus 4. So that would get us, instead of squared would be to the 4th power, it'll knock it down to the 3rd power. All right, well that's a little bit. Let's keep going with our simplifying. Minus 4x times x squared, minus 4x cubed, minus 4x times 4, minus 16x. Then we have the minus, and don't forget it's going to go through to both terms. There's a 2 and a 2x. So let's work it out here. Minus minus makes plus. 2x squared times 2 is 4x squared times 2x. Will get us up to 8x cubed. And then minus 8 times 2 times 2x. So that would be a minus 32x. And that's divided by x squared plus 4 cubed. Well, okay. That would be, that's 4x cubed, because 8x cubed minus 4x cubed, minus 16 minus 32 is minus 48x. And divide that by x squared plus 4 cubed. All right, well, let's go ahead and factor. That's 4x times x squared minus 12 divided by x squared plus 4 cubed. Now, x squared minus 12, maybe not the most pleasant thing, but it can be factored. It's actually not so hard, especially if we think of it as a difference of squares. So we can think of this as 4x x minus square root of 12, x plus square root of 12. And divide that by x squared plus 4 cubed. If we come up here, we can do something similar. Minus 2 times x squared minus 4. And then what happens is, well, that becomes x minus 2, x plus 2. Divide that by x squared plus 4 squared. All right, so we have our first derivative, we have our second derivative. Now, where are the interesting points? The interesting points would be where the derivative, our second derivative, is equal to 0. So, where does that happen? Well, let's make our dots. Because remember, we're playing a game of connect the dots. Our first derivative, well, 2 or negative 2. That could be where we have something interesting going on. Our second derivative would be at 0. Ah, that's nice. It's always nice when you have 0. And at square root of 12. And at minus square root of 12. Okay, so in terms of graphing the function, there are 5 interesting points. That's a lot of points when it comes to graphing. Well, let's see what we get. Now, plug in 2. That'll be 2 times 2 is 4. 2 squared is 4, plus 4 more. That'd be 8. So we have 4 over 8, also known as 1/2. Okay, all right. How about negative 2? Now, let me pause for a second and say, this function, it's kind of a curious function, a peculiar function, strange, unusual. Some people might even say that this function is odd. It's an odd function. Can you see that? You see what happens? If I plug a negative into a square, it doesn't matter whether it was negative or positive before. It's still the same outcome. But upstairs, if I plug a negative in, I flip the sign. So the net result is plugging in a negative is exactly the opposite sign of plugging in the positive. That's what it means to be an odd function. Since I know what happens at positive 2, at negative 2, something similar, just opposite sign. Plug in 0, very easy because our numerator is going to be 0. All right, how about square root of 12? Well, that one we've got to think a little bit about. So downstairs, it's actually not so bad. We have square root of 12 squared. It's 12 plus 4 is 16. And then upstairs we have 2 times the square root of 12. So that would end up being 1/8 square root of 12. All right, and then similarly, negative 1/8 square root of 12. Okay, so there are our dots. All right, well, let's mark these. So now, at some point, you're going to say, what is the square root of 12? You can make a little bit of a note here. Square root of 12, notice that 4 divides into 12. So this is the same as the square root of 4 times the square root of 3, which is 2 times square root of 3. And, of course, that only helps if you know what square root of 3 is. Well, it's about 1.7 something. So roughly speaking, we're going to think about 3.45-ish is the ballpark that we're going to shoot for. All right, 3.4, 3.5, one of the near there. We don't need to be exactly right. We just are looking for a good rough representation. So let's draw ourselves a grid. And we're going to mark our points. So we're going to say, okay, here is 0, 0. Okay, so we said it's about 3.4 or 3.5. So 2.5 will come next. So let's say this is at 2.5. And then 3.4, give or take, something, that'd be roughly somewhere, 1/8. That's going to be a pretty small number. I'll say roughly like right here. Of course, then we have the symmetry. So we have something like that. There are our 5 points. We can already have a pretty good sense now of what's going to happen. All right, now let's talk about what's happening to our derivatives. So if you go through, we can use symmetry because let's talk about our first derivative. Our first derivative, it's an even function because all the powers are x squareds. So that says whatever happens to the derivative on the right is the same as the derivative on the left across. So let's plug in something like 1. What happens? Well, negative 2 plus 8 is positive. So we see, y prime is positive here. And, all right, what about the second derivative? I'll plug in 1. Now, I guess I should pause and say the second derivative is an odd function, right? Because, you see, odd powers upstairs means it's odd upstairs, even downstairs. So, net result, it's an odd function. Okay, good. So, we say, all right, what happens, say, at 1, right? So, plug in 1, 4 minus 48, negative. So, we're concave down. Now we come over here, that says, hey, y prime still positive, but y double prime is now also positive. Because symmetry says you don't change y prime, you do change y double prime. Now, to help you understand what's going on here, I just want to make clear what I'm doing, is I'm trying to understand the behavior in these pieces here. Okay, and if we do that, then we'll get a really good sketch at the end. Okay, well, let's just say we're just barely over 2. Okay, what happens? In our first derivative, well, we'll see if we're a little bit over 2. We have a negative, Then here, positive and positive, which means that we're going to be decreasing. Y prime will be negative, which means we're also negative over here. If I plug in something really large, 100, same thing. So I'm negative, and therefore I'm also negative over here. Okay, now how about the second derivative? Well, the second derivative, see, 2 doesn't really do much. We don't change the second derivative until square root of 12. So the fact that our second derivative is negative before 2, just before 2, it'll still be negative just after 2. So y double prime still negative. Over here, y double prime positive. Now, what happens in the long run? So a very large value. So, 1,000,000. All right, or 4. But anyways, if you pick a very large value, what you'll see is that the x cubed term dominates, so you're going to be positive. So our second derivative will be positive. On the flip side, that means our second derivative is negative. Okay, so that's all our points and all our intervals. We understand how everything behaves. One other thing we can make an observation of is we know the long-term behavior. We can see it because as I let x get big, positive or negative doesn't really matter. The downstairs is much bigger than the upstairs. So asymptotically, it should approach 0. So I should be approaching this line. All right, so we put it all together, and what do we get? Well, I'm decreasing concave down, and I'm coming off of 0. So I'm doing this to here. Now I'm decreasing, but concave up over to here. And this, by the way, is a place where the derivative is 0. So that means I'm going to go here, up, and then sort of flatten out. Now, increasing concave up. So, increasing concave up. Then I'm going to be increasing concave down. And I should actually say at this point, I can just now do the symmetry. If I know what it looks like here, it's going to be the same picture. Decreasing, and I'm concave down. So, and then here, I'm going to be decreasing but concave up, and I need to approach that asymptote. And there you go. There you go. So there's our local max, our local min, and these are all inflection points. So I guess we should make a little note. This is a local max, local min here. Here's a local max here. This is an inflection point because we do change concavity. This is an inflection point because we do change concavity. And here's an inflection point. And all right. Wow, cool. See, we can do it. Maybe not as fast as a computer, but to be fair, the computer is doing a lot more computations than we are. We're being a lot smarter about our computations. It's, think smarter, not harder. All right. Well, thanks for being so patient and sticking into the end, and keep that practice going. You're going to do it. I believe in you. Keep it up.